This is Harshini. Today I am going to explain about how to represent graph using adjacency matrix and incidence matrix. But before going to graph representations, let us discuss about what is meant by graph. What is graph? In data structure, a graph is a non-linear structure that consists of vertices and edges that connect them. Now here is an example of graph. Here A, B, C and D, E are called vertices and lines joining those vertices are called edges. So where we use graphs in real world scenarios like in social networks, representing connections between people, route optimization, finding shortest paths in maps, getting suggestions of nearest restaurants, cinema theaters, and etc. etc. Three types of graphs are divided into two: directed and undirected graphs. Directed graph, it is a set of nodes or vertices that are connected by edges where the edges have a direction associated with them. Whereas in undirected graphs, here the edges between vertices do not have a direction and can be traversed in both the directions. Our main topic is graph representations. Let us briefly discuss about it. We can represent graph in two ways using adjacency matrix and incidence matrix. Now, what is meant by adjacency matrix? It is representation of graph as a matrix of Boolean, that is zeros and ones. To implement adjacency matrix, we create 2D matrix of order n cross n if there are n vertices in the graph. If there is an edge present between two vertices, we mark adjacency matrix as 1. If there is no edge present between two vertices, we mark adjacency matrix as 0. Imagine a graph as a map with cities, that is vertices, and roads, that is edges, connecting them. And adjacency matrix is like a table that shows which cities are directly connected by them. Representation of directed and undirected graph using adjacency matrix. In undirected graph, there are 5 vertices. So size of the matrix is 5 cross 5 as there are 5 vertices. For A, there is no edge with A. So we mark it as 0. For A, there is an edge between C and B. So we mark it as 1. And there is no edge between D and E, so we mark it as 0. Similarly, we do for B, C, and D and E. In directed graph also there are 5 vertices. So the size of the matrix is 5 cross 5. There is an edge between A to A, so we mark it as 1 here. For A, there is an edge between C and B, so we mark it as 1. There is no edge between A to D and A to E, so we mark it as 0. Similarly, we do it for B, C, and D, E. So the final adjacency matrix would be this. The implementation of adjacency matrix in undirected graph. First, we have to create a 2D matrix. Use it to represent a graph. Each cell in the matrix indicates the presence or absence of an edge between two vertices. The main logic is if there is an edge between two vertices, we mark the cell as 1. If there is no edge between two vertices, we mark the cell as 0. Here we have initialized number of vertices to be 4 and number of edges to be 4. Each directed indicates whether the graph is undirected or directed graph. Edges is a 2D array. It stores the source and destination vertices for each edge. Now we create 2D array, that is adjacency matrix. The size of the matrix is number of vertices cross number of vertices. We create a loop. This loop iterates over each edge in edges array. And here for each edge, source and destination vertices are extracted. For loop starts with I equal to 0. This means we are considering the first edge in the edges array. Edge of I refers to the first element of edges array, which is 0, 1 in our case. Here, this line, source equal to edges of I0, this line extracts the first element from the current edge and assigns it to the source variable. Since the first element of 0, 1 is 0, the source is assigned the value 0. And next line, destination equal to edges I of 1. This line extracts the second element from the current edge and assigns it to the destination variable. In this case, destination variable is assigned the value 1. Now the source and destination vertices are extracted. The vertex indices are validated to ensure they are within the range or not. Here, if condition is used to validate the vertices. If the vertices are valid, a 1 is placed in the adjacency matrix, that is source to destination, indicating an edge from source to destination. If the graph is undirected, a 1 is also placed in the adjacency matrix, that is from destination to source, to represent the bidirectional edge. Next, we display the adjacency matrix right. Now, let's see limitations of adjacency matrix. Space complexity. It requires order of v square, where v is the number of vertices. Even there are few edges, it requires lot of space. So, to add any new elements, it takes so much of space and time. So, therefore, it is less memory efficient. It is of fixed size. Size is fixed to vertices cross number of vertices. So adding or removing vertices can be inefficient and require matrix resizing. Inefficient edge search. It is of searching for all edges connecting to a vertex, requires checking each cell in its row, which can be time consuming in large matrices. We have completed adjacency matrix. Let's discuss about incidence matrix. An incidence matrix is another way of representing a graph using a matrix format. In an incidence matrix, rows represent the vertices of the graph, columns represent the edges of the graph. Each entry in the matrix tells us whether a particular vertex is connected to the particular edge. Representation of incidence matrix in undirected graph. In an undirected graph, the entry is 1 for both vertices connected by an edge. If there is no edge, it is 0. Let's see the example for undirected graph. E1 is the edge which connects V1 and V3. Therefore, here 1 is placed over here. For V3 also, here 1 is placed. E1 do not connect with V2 and V4. Therefore, it is 0. Similarly, we do the process for E2, E3, E4 and E5. Let's see representation of incidence matrix in directed graph. In a directed graph, the entry is 1 for the starting vertex and -1 for the ending vertex of the edge. If there is no edge, it's 0. So now let's see an example to understand this. So here we can see that E1 is the edge that is connecting between V2 and V1. V2 is the initial vertex and V1 is the final vertex. We know that for initial vertex it is 1 and for final vertex it is -1. So we can see in the column of E1, for V1 it is -1 and V2 it is 1. Similarly for E2, E2 is an edge between V1 and V3. Here V1 is the initial vertex and V3 is the final vertex. So for V1 it is 1 and V3 it is -1. For V2 and V4, there is no edge E2, therefore it is 0. Similarly, we continue this process for V3 and V4. We get this incidence matrix. Now let's see implementation of incidence matrix using Java. Implementation of incidence matrix in undirected graph. We know that for an undirected graph, both vertices connected by an edge will have a 1 in edge column, indicating that they are both connected by this edge. We declare three fields: vertices, edges, and incidence matrix. It is a 2D array. Here, this is a constructor of the class. It takes vertices and edges as parameters and initializes these dot vertices and these dot edges with the input values. Incident matrix as a 2D array with the vertices as rows and edges as columns filled with zeros by default. The add edge method connects two vertices by setting ones in the instance matrix. Vertex 1 and vertex 2 are the indices of two vertices connected by edge. Edge index is the index of the edge in the matrix. This method sets 1 in the matrix for both vertices at edge index, marking their connection by this edge. Now display matrix method prints the incidence matrix. It loops through each row that is representing vertices and each column that is representing edges. For each element, it prints 1 or 0, showing whether each vertex is connected by each edge. Now, this for loop iterates over each edge, prompting the user to enter the two vertices that each edge connects. Vertex 1 and vertex 2 are read as input and represent the indices of vertices connected by the edge. Add edge is also called with these vertices and the current edge index I, which adds the edge to the incidence matrix. Now let's see code for the directed graph. The code is similar to undirected graphs. So just a similar change is there in undirected graph we have vertex 1 and vertex 2. In directed graph we have starting vertex and ending vertex. So minus 1 is placed for the ending vertex of the edge and 1 is placed for the starting vertex. This notation helps to identify the direction of each edge. Each column in the matrix represents an edge with the direction from minus 1 to 1. Now let's discuss about limitations of incidence matrix space complexity. For a graph with V vertices and E edges, the incidence matrix requires order of VP space. This can be inefficient for large graphs, especially if the graph is dense or has many vertices but few edges. Edge lookups. Checking if two vertices are connected by an edge requires scanning through all edges, making it less efficient for direct edge lookups compared to an adjacency matrix. It lacks direct information on vertex degrees. The degree of a vertex is the number of edges connected to the vertex. In an adjacency list, each vertex has a list of all adjacent vertices. For example, if vertex A has a list of neighbors B, C, D, then A has a degree of 3. This is a direct and efficient way to determine the degree of a vertex because the adjacency list inherently organizes each vertex neighbors. An incidence matrix, on other hand, does not explicitly list each vertex neighbors. Instead, it shows which vertices are connected to which edges. So each column represents an edge between vertices. To find degree of a vertex in an incidence matrix, in directed graphs, out degree and in degree have to be calculated separately by counting minus ones and ones respectively. This matrix does not directly list neighbors, so you have to scan through each row to count the edges. Directed edge complexity. For directed graph, the matrix must include values like minus 1 and 1 to distinguish start and end vertices, which adds complexity to interpreting and maintaining the matrix. Now let's see uses of incidence matrix. Incidence matrices easily represent multi-graphs as each edge has a dedicated column. Graph theoretic algorithms. In this, certain graph algorithms such as those for network flow, circuit analysis, and matching problems use incidence matrices because they focus on the relationships between edges and vertices. Efficient edge traversal. If algorithms require frequent traversal of all edges rather than vertex specific edges, the incidence matrix can be useful because each edge is clearly represented by a column. Bipartite graphs. Incidence matrices are particularly useful in representing bipartite graphs where the vertices can be split into two sets with edges only running between the sets. The incidence matrix clearly shows these connections without redundancy. Now let's compare adjacency and incidence matrix in terms of matrix dimensions. In adjacency matrix, its size is based on the number of vertices. So it's a square matrix with rows and columns equal to the number of vertices. In incidence matrix, its size depends on both the number of vertices and edges. It's a rectangular matrix with rows for vertices and columns for edges. The purpose of entries. Each cell shows if there is a direct connection between two vertices. For example, if there is an edge between vertex A and vertex B, the cell for A and B will have a 1. Whereas in case of incidence matrix, each cell shows which vertex is part of an edge. For each edge, the column mark the vertices it connects. So, for example, if edge 1 connects vertex A and vertex B, both A and B will have a 1 in the column for edge 1. In values in cells, in adjacency matrix, a cell is 1 if there is a connection and 0 if there is none. In that undirected graph, it's symmetric because connections go both ways. Whereas in incidence matrix, a cell is 1 if a vertex is connected to an edge. In directed graph, it's 1 for starting vertex and -1 for ending vertex. Whereas in memory usage, adjacency matrix takes up more space, especially if you have a lot of vertices because it creates an entry for every possible pair of vertices. Whereas in incidence matrix, it uses less memory if you have fewer edges than vertices. Each edge gets its own column, so few edges mean few columns. Edge lookup speed. In adjacency matrix, you can quickly check if two vertices are connected by looking at a single cell, which is very fast. In incidence matrix, finding if two vertices are connected by an edge is slower as you need to scan through column to see if they share the same edge. Degree calculation. To find the degree, just we have to add up the numbers in the row for that vertex. Each one means a connection. In incidence matrix, to find the degree, count how many ones in undirected graph or 1 and -1s for directed graph are in the row for that vertex. Symmetry in undirected graphs. Adjacency matrix in undirected graph, the matrix is symmetric, meaning if there is a 1 at I comma j, there will also be a 1 at j comma I. Incidence matrix not symmetric as each column only represents one edge with its own start and end vertices. Best use cases in adjacency matrix, it works well for tasks needing fast access to connections like checking paths or finding connections between specific vertices. Incident matrix, it is useful for problems focused on edges like analyzing networks or representing graphs with multiple edges between the same vertices.